Okay, well, we're going to talk about how to transform and how to draw basic graphs of exponential functions. And what we have right here is a very basic graph, 3 to the x, very common function. And in understanding this, we have a base which is going to be greater than 1, so we know it's going to be an increasing exponential. Sometimes we refer to this base as a, so if you have a is greater than 1, all right, whereas this can be a to the x, wherever that one can be. We know that a can't, or the base cannot equal 1. It has to be greater than 0. But in this case, because the base is greater than 1, it's going to be an increasing exponential. Different properties that we know about exponentials is the basic parent functions of this, which we're going to be transforming a little bit, have a y-intercept. In this case, it's going to be right here at 0, 1. And we also have a horizontal asymptote right here at y equals 0. And it goes on to infinity for the right end behavior, goes into infinity like so. All right, and we're going to take this graph, we're going to transform it. And we're also going to find the domain and range. Now, the domain of basic exponentials, you can see is going to be all real, because there's any value you can plug into exponential function. There's no value it cannot. The other thing is the range. For a basic exponential, you can look at it and say, okay, all y values have to be greater than 0. You can't equal 0 because there's a horizontal asymptote right here as x goes to infinity. So we get a horizontal asymptote to the left-hand behavior. So how is this graph being transformed in these next 4 examples? So our first example, we have 3x plus 1. Well, this x plus 1, what that means is that we are shifting this graph to the left 1 unit. Okay, 1 unit. So that means all the points on that original function are being shifted to the left. So that original y-intercept is going to be moving over to right here. Okay. We can find the new y-intercept. If you want to know the new y-intercept, depending on what you have to do, just plug in x equals 0, and we can see that it's going to be y is going to equal to 3. So if you want to plot that, you can plot that right there, and you can see that we're going to have a graph that looks like this. Has the domain changed for this function? No, the domain stays the same. Still can plug any values in it. Has the range changed? Well, we can still see that we have y equals 0 as my horizontal and behavior to the left. And so we're going to have y values are going to be greater than 0 is my range. Okay, well, we can move on. We can talk about another one. This one is a little bit more difficult. It has 2 different transformations. We have one right here where we're going to be reflecting all the y values are changing to the opposite, so it's a reflection over the x-axis. We also have this right here where we're moving all the y values up 5. All right, the graph's moving up 5. So when we graph this, we can see that since we are reflecting it, this point, which did start here, all right, at 0, 1, is now reflected and going to be at 0, negative 1. We are then going to move all the values up 5 so that this new point is going to be moved at 1, 1. If you can see this 1, I'll move that 1, 2, 3, 4, and 5. So when we have that, we're going to have 1, 2, 3, 4, and 5. So we're now going to have a value at 0. It appears 4. Okay, to figure this out, we can plug in a 0 value in there. And so if you want to find a new y-intercept, x equals 0, you get negative 1, and it's going to be 4. So that does make sense. We also have our y horizontal line. This horizontal line starts at 0, but it's moving up 5. So we're going to go 1, 2, 3, 4, 5. And you notice that this horizontal line is actually going to equal whatever the vertical shift is. Since it goes up 5, my new horizontal line is at y equals 5. So that's a key thing to kind of note, is that this right here, the movement is equal to the horizontal. That's a key thing. So when we do our graph, we can now see that I'm going to change colors. I'm going to get red now. Okay, so we see this new transformation is going to go like so, and then it's going to go down because it's reflected. And we can see our domain is once again all reals. My range, however, does change because now we see that our horizontal line is at 5, so and it goes down, decreasing. So it's y values which are going to be less than 5. All right, so that's that graph. Moving on to our next function, next pair that we're going to look at. All right. We have this graph where we have, again, two transformations. This one is moving to the right 2, and also moving down 2. So as we graph this function, we can take our original 0, 1, our y-intercept, and it's moving to the right 1, 2. And then it's moving down 2, so 1, 2 down here, and so we have this other point. We can find our new y-intercept. If we want to put x equals 0, we get 3, and then the second power, minus 2, which is going to be a kind of a smaller negative value, all right, because we have 1/9 minus 2, and so that's going to be, okay, add the exponents, so it'd be 18 ninths, and what we have then is negative 17 ninths. Okay, and we can plot that if we wish. Okay, and the next one that we have is we're going to also move, all right, moving down 2. And if you remember from our previous example, that means we're also moving our horizontal line. So when we have this right here, we're going to move this how many times we have a vertical shift. So in this case, our vertical shift is moving down 2. So we should have this right at negative 2, y equals negative 2, because once again, the horizontal asymptote matches the vertical reflection, or sorry, vertical shift. So nothing else has changed. This is an increasing function, so we have a graph that would look like this. All right. Domain, all reals. Range, we can see now, starting at y values are going to be greater than negative 2 in this case, because that's where our horizontal asymptote will be. All right. Our final example, here, and I'll make this one in green, is we once again have two different functions, or two different transformations, or translations. This one right here, we're reflecting over the y-axis, and we also are moving this down 6. Down 6. Now, you can also think about this vertical reflection. Because we have the negative exponent, negative exponents can be rewritten. And we can rewrite this as f of x equals 1 over 3 to the x minus 6, which can also be written as 1/3 to the x power minus 6. That's another way of writing it, which tells us that this, instead of being an increasing function, is going to be a decreasing exponential. So however we want to do it, that's fine. But we're going to start with our basic common function, which we know starts here. And what we're going to do is reflect this over the y-axis, so this doesn't change. But then what we're going to do is move this down 6. All right, down 6. So we're going to go 1, 2, 3, 4, 5, 6. And you can see that's going to be at, we're plugging that 1 and be at negative 5. 1, 2, 3, 4, 5, negative 5, of course. And now we're going to move our horizontal asymptote, and that should, once again, horizontal asymptote equals whatever we're shifting it down. Let me move that right there, because that's what we're doing. And so we should have this right here being at negative 6. So, oops, let me take the other one. 1, 2, 3, 4, 5, 6. So we have this y equals negative 6. And we are having a decreasing graph. It's reflected over the y-axis. And that's our new function. Domain, all reals. Range, well, we can see because, once again, this equals wherever vertical reflection is, our range is going to equal y is going to be greater than negative 6. Okay. So we've gone through 4 different examples of how to graph exponentials, given the common function of how a common function looks by looking at the horizontal asymptote, where it increases without bound to the left side if it's an increasing function, and also finding the y-intercepts. I hope this helps out, and good luck with the rest of your problems, and God bless. on the rest of your work in mathematics.